Jonathan and I were asked to talk in this session and do a little tutorial on a number of different topics, including the quantum mechanics of black holes, unitarity, the firewall paradox, and we were also asked to speak about Penrose diagrams, these strange space-time diagrams that you may have seen written down. That is a preposterously large number of topics for 1 hour, and really this time is for you, and we are at your disposal. And I don't even know if the most thing you'd be most interested in is to do a sort of ask random questions about black holes session. The way we'd thought to divvy up the time, if we don't want to do that, is that I'll speak hopefully for just a short time about sort of intro to the quantum mechanics of black holes, and then Jonathan will take over and tell you about some more advanced topics in the quantum mechanics of black holes, and then if there's time at the end, I'll tell you about these conformal diagrams and what those mean, though that's a somewhat specialist topic. Does that work for everybody?
Sounds like a creditable solution to an impossible problem.
Okay. Okay, so black hole entropy. So what is a black hole? A black hole is a object that has undergone gravitational collapse and has so much gravity and is so dense that it's actually impossible to escape, even if you can move at the speed of light. And so when we say the size of a black hole, what exactly do we mean by that? What we mean is the size of the event horizon of a black hole. So this is a spatial picture of a black hole, and so here's the black hole. And this is the event horizon. And the event horizon is not where the matter lives. We think that the matter in a black hole, the things that used to make up the star that underwent gravitational collapse and formed a black hole, lives at the very center, if it can be thought to live at all, at what's called the singularity, at a tiny point-like thing right at the very center where all of the matter collapsed to. The event horizon, though, shrouds the singularity. What the event horizon is it's the point past which, if you go, you will never be able to get out again. You will never be able to escape. So that's what the event horizon is. And the thing you need to know about where the event horizon lies is the following. That the area of the event horizon, 4 pi times r squared is the area of the event horizon. R in that formula is given by 2g, which is the Newton's constant, times m, the mass of the black hole, in units where c equals 1. Okay, and so when I talk about the size of the black hole, I really mean the size of the event horizon. Now, nobody really thought to put thermodynamics and black holes together until Bekenstein in the 70s. But you're sort of familiar, of course, with the second law of thermodynamics that says that entropy always increases or never decreases. But there's a sort of thought experiment in which you can decrease the entropy of the universe, which is you take a boiling pan of gas and which has some high entropy, and then you throw it into a black hole, and now you don't have the gas anymore, and now the entropy of the universe has gone down, and you violated the second law of thermodynamics. Yeah?
If you took the old-fashioned frozen star view, would the entropy go down in that case?
Well, you might melt the frozen star in that case. Well, let's not talk about the frozen star.
Sorry, this is just the one where you think everything when a black hole's collapsing, it's just slowing and slowing down, right? And there's nothing actually frozen about it. It's just that the time dilation is going to infinity.
Let's not get on to these other models of black holes. What you're going to have to say, let's go with the Einstein picture of black holes.
This was the Einstein picture. But
let's not.
This is not an alternative model of black holes.
Okay. Okay, well, I'll tell you about black holes then. So we know that black holes must therefore have an entropy. And the question is, how much entropy can they have? If they didn't, we could violate the second law of thermodynamics. And so we've the entropy of a black hole being 0 is something we've just ruled out, because if the entropy of black holes were always 0, that we could violate the second law of thermodynamics. So given Now, there's another fact you need to know about black holes, which is that if you're sitting outside them, basically the only thing you can see is their mass. There's no other property of them, unless they have charge or spin, that defines them. So it can only be the case that the entropy of a black hole is a function of its mass or its radius. Yeah.
Sorry to ask the same question again.
Right.
Which is, we talk about what kind of entropy?
Here I'm talking about coarse-grained entropy. So this is not the von Neumann entropy of a black hole. The von Neumann entropy of a black hole will come up later, but it's not the von Neumann entropy of a black hole. It is the same sense in which, if you were doing conventional thermodynamics, to do with steam engines and all the rest, if even if the whole steam engine is in a pure state, or the whole chamber of gas is in a pure state, it doesn't have entropy 0. It has 0 von Neumann entropy, but it has a non-zero coarse-grained entropy. And so that is the quantity that obeys the second law of thermodynamics, that has an entropy that increases. And so that's, if you're trying to track the second law of thermodynamics, that's the quantity that you're interested in. Yeah.
Okay, so once you see, once this entropy is sucked down into the black hole, what's the point of, and it's not interacting with the rest of the world, what's the point of still considering it as counting with it?
Yeah, so you might just say it's gone, don't worry about it. And that's a bit disappointing because it means that you can't use the laws of thermodynamics anymore when black holes are around. So you might aspire that there is a law of thermodynamics that applies even in the case where black holes exist, and the good news is that that aspiration has been realized by the intellectual edifice I'm about to present. Okay, so let's just write down some other possible theories, one of which is S equals infinity.
Just a very quick question.
Yeah.
How big are these black holes? Like, is there any range?
Yeah, there's a range. So the black hole is, how big it is determined by its mass through this formula. So if I stick in one solar mass here, I get that it's about 1 mile big. So many of the supernova remnants are one solar mass or a few solar masses, and so they're measured in miles. If at the center of our galaxy there's million solar mass black holes, so that's measured in millions of miles. In principle, I can plug anything I like into this formula.
Small.
They can be arbitrarily small, though if they get too small, then quantum effects start to become important. But they need to get really small before quantum effects start to become important.
I thought we were going to measure in SI units.
Yeah, 1.6 kilometers, yeah, or 1,600 meters, I guess. Okay. So S equals infinity is another option you could say, which I think basically boils down to your suggestion, but we're not going to do that because then you can't really use the second law of thermodynamics, and in any event, that turns out to be wrong.
Miles too large.
Right. So I'm just going to sort of talk about 3 possible options, but I'm not going to do this for too long. Those seem like 3 possibilities. S equals R is actually experimentally ruled out. If you remember LIGO, it saw a 30 solar mass black hole meet another 35 solar mass black hole and make a 62 solar mass black hole. What happened to the conservation of energy in this equation? Great, yeah, plus 3 solar masses worth of gravitational radiation that went off. Gravitational radiation has a tiny entropy by these standards, so it better not be the case that the entropy of a black hole is linear, otherwise this would just have violated the second law of thermodynamics, this LIGO black hole meets black hole collision. So in fact this turns out to be out. Obviously this does not violate either of these bottom 2 rules though, because 62 squared is indeed bigger than 35 squared plus 20 squared, 30 squared, and same for the cubes, yeah.
So is the radius like the only number that determines the entire black hole?
Correct. In terms of the coarse-grained quantities of the black hole, the only thing you need to know is the mass, the radius. Unless there are conserved charges that you've thrown into a black hole, like electric charge, or the black hole is spinning. But in those cases, you just need to know those. So there's up to 3 you need. But it's like you have a we're doing the same as like steam engine thermodynamics. In terms of the macroscopic properties, even though there's Avogadro's numbers worth of stuff going on, you only need to know a few coarse-grained properties in order to know the thermodynamical properties. Yeah.
So the horizon is basically just a property of the curvature. That when it gets, too curved, then you can get out or something.
That's sort of, but not exactly true. So the curvature is actually not that large at the event horizon in terms of the invariant space-time curvature. The thing that's large is the gravitational, is the rate at which you'd have to fire your rocket in order to get, in order to not fall into the black hole. So the rate at which you have to fire your rocket, in other words, the proper acceleration, goes like, it goes like the mass of the black hole over r squared, that's just the normal Newton's law, I guess, g, times 1 over root 1 minus 2gm over r. In other words, normal Newton force when you're a really long way away, but when you get close, it gets magnified by this extent. But the curvature itself is not blowing up. So the proper acceleration required to stay static that's blowing up.
Maybe.
The gravitational field is blowing up, but not the curvature.
Still, was going in a different direction. This is also interesting. But somehow, there can't be any other shaped black hole because now you say the only parameter is r, and then it's just a sphere.
Yeah, it turns out black holes settle down to spheres very quickly indeed. If you make a black hole and you make it an oblate spheroid, it'll just ring down immediately, gravitational radiate away all those higher moments, and it'll become a sphere almost immediately. So, I mean, if I throw something in, it'll ring, but it'll ring for a time that goes like r log r, which is a very short time indeed. So for a solar mass black hole, that's much less than a second. Much less than a second. Right. Okay, so this rules out this, but it still leaves these two. This, if you're used to thermodynamics of gases, might be what you would expect, that if I have a box of gas at some temperature, the entropy is extensive. It's just still like the volume. If I take two things at the same temperature and put them together, it should scale like the volume. But the most profound fact we know and are sure about quantum gravity, the thing that we have discovered in the 1970s that is the most assured and remarkable fact about quantum gravity, is that this is wrong and this is right. And a hint that this is the right answer, that in fact was what tipped Bekenstein off when he first proposed this answer. A hint is provided by a rule of classical general relativity. So Einstein's theory that tells you how gravity works. It's called, that was proved by Hawking also in the earlier 1970s, or maybe even the 1960s, which is the Hawking area theorem. Which says that black hole areas, this is in classical general relativity, no quantum mechanics involved here. Black hole area, the total area of all the black holes in a system, that under the evolution of general relativity, the rate of change of black hole area needs to be greater than or equal to 0. It never decreases. Which is a striking fact, yeah. This was a theorem proved by Hawking, who did not have thermodynamics in mind at all, that the rate of change of black hole area always increases. And this is a non-trivial fact, because if I take two black holes and smash them together, then like the mass of the black hole that can result is smaller than the mass of the two constituents, but the area of the black hole will always be bigger. And we can test this in all...
Volume, it wouldn't be true.
The volume actually would also be...
Okay, the volume is still in zero.
Yeah, I think the volume would probably also be true. Maybe I could come up with situations in which that wouldn't be right. I need to think about that. Because you could spin a black hole. One thing you can do with a black hole is spin it and...
Until it breaks.
Well, actually in 3+1 dimensions you can't break it, but in higher dimensions you can break it. And then I'd need to think about whether the volume is Yeah, good question. Yeah, that wasn't meant to rule out that, but maybe it actually does. But anyway, this is the theorem. And so that sounds an awful lot like entropy always increasing. And so in fact, the conjecture that Bekenstein made is that the entropy of a black hole, again, I mean the coarse-grained entropy of a black hole. So BH stands both for black hole and also Bekenstein-Hawking, the two discoverers, which is one of nice features of...
No, that's too much fine-tuning.
Right. Is that it goes like r squared. Or should we say goes like 4 pi r squared, like the area. Okay, now you need to ask what else do we need to do? Entropy has no units. It's a dimensionless quantity. This has units of area, so that this doesn't work on its own. You need to add things, and the ingredient list, the menu of possibilities, are G, H bar, and C. Now C is 1, so that's not going to help, and I'm not going to worry about that. That leaves over G and H bar, and it's a matter of dimensional analysis to figure out that the only combination that will turn you from an area into nothing is H bar and G. Not for these purposes.